So this talk is about tetrahedra. So over here on the left, I have a regular tetrahedron. So this is formed of 4 equilateral triangles, and it's a solid figure and it's bounded by these 4 equilateral triangles. So it's in Dungeons and Dragons, it's also known as a D4, a 4-sided die. But you can also have non-regular tetrahedra. So a tetrahedra can be any solid figure that's bounded by 4 triangles, like this one here. And I'm going to ask, well, it's not my questions, but there are 3 old questions about tetrahedra and 2 of them are still unsolved. And so I want to explain what these are, and I'll explain these terms that I'm using in these problems. So the first problem is about filling space with tetrahedra. The second one is about cutting up tetrahedra and reassembling them into a cube. And the third one is about what are called dihedral angles. And dihedral angles are the angles that are formed. Well, di means 2 and hedral means side. So it's the angle formed by 2 sides of a tetrahedron. So for example here, well, maybe it's a little bit hard to see in this picture, but if you imagine this front triangle here, and then there's also the back triangle, then they sort of join along a hinge. And if you imagine that you could swing that, then the dihedral angle measures how open that hinge is. So it sort of measures how close together those faces are. So for another example, in this one, this dihedral angle between these 2 faces, that's a very small dihedral angle. All right, so let me get started with these questions. And for each of these questions is in 3 dimensions because it's about tetrahedra. But you can also ask the analogous questions in 2 dimensions. And so as a warm-up for each of these, I'm going to start with a 2-dimensional problem. So let's talk first about filling the plane and with copies of an equilateral triangle. So here's an equilateral triangle. And well, I think you all know that you can fill the plane by taking congruent copies. So congruent just means it has the same shape and size. So you can fill it like this. Don't worry about the color. The point is that all these triangles are the same shape and size. They're just maybe rotated or translated around. But yeah, so you can fill the whole plane that way. Okay, suppose you had a triangle that wasn't equilateral. So here's another. So suppose you had a triangle of any shape. Can you fill the plane with copies of that one? Well, the first thing you can do is you could take. If you imagine this midpoint of this side here, if you rotate this triangle 180 degrees around here, you'll get another triangle. And then once you have those 2 triangles, you can take this sort of domino kind of thing and translate it around to then fill the whole plane. So the answer is yes. So all these triangles in this picture are again congruent to the original one. And so yeah, so in 2 dimensions, any triangle works. You can always tile the plane. So, okay, but now let's move on to 3 dimensions. And so where we're going to, instead of a triangle, we're going to talk about a tetrahedron. And the ancient Greeks were interested in this, about whether you could fill space with copies of a tetrahedron, because Plato had a theory of matter, so an atomic theory, where he postulated that that each of the 4 elements, which I've listed here, had its properties because it was composed of lots of microscopic regular polyhedra all packed together. So for example, Earth was if you imagine that Earth was a bunch of cubes all packed together. And same for all the other ones. He even had some intuitive explanations for why, like which ones should be which. For example, he said that the reason that fire hurts your hand is because, well, it's got all these microscopic sharp points, and so that's why fire. Yeah. So yeah. Oh, there's also a fifth one. I mean, that one he just said is what the cosmos is made of. This universe. Okay. So, well, Aristotle did not appreciate this. He thought this was not a good theory. And I mean, he didn't complain about the fire having lots of sharp points hurting your hand. That's not what he complained about. What he complained about was, well, in Aristotle's theory, in physics, you were not allowed to have gaps between particles. There is no such, you could not have a vacuum. Everything had to be filled with something. And so said, okay, Earth is okay. I mean, to have Earth be the cube, that's okay because you can fill space with that. But some of these other ones, they don't fit. You can't pack them together. So, I mean, there will always be gaps. For example, if you take this icosahedron, you will not be able to fill space with those. And so he objected. He said that cannot be what matters, what these elements are made of. Because he said, oh, well, the cube you can fill space with, and the tetrahedron, the regular tetrahedron you can fill space with, but the other ones, you cannot do it. Okay, so that's the ancient Greeks. And then 1800 years later, Johannes Müller said, well, you notice that this is not actually, what Aristotle said is not true. So it is true that you can fill space with cubes, but you can't actually fill space with regular tetrahedra. And so I guess this is just, I mean, I don't think he actually used these exact words, but anyway, but you get the idea. I mean, I guess it just goes to show that when you have somebody in a position of authority saying something false, it sometimes takes a long time for to get the record straight. Okay, anyway, let me go on and explain why regular tetrahedra can't fill space. It has to do with the dihedral angle that a tetrahedron has. So remember, the dihedral angle is the angle between two faces. And because it's regular, all the dihedral angles here, all the 6 dihedral angles are the same. Now, if that dihedral angle for a regular tetrahedron were 60 degrees, well, then you could take 6 of those tetrahedra and fit them around an edge, and they would fill space, at least locally, around that edge. But the actual dihedral angle is a little bit bigger. If you work it out, it turns out to be a little bit more than 70 degrees. In fact, it's not even a whole number. It's not even a fraction either. It's not like 70 and plus a half. It's just some strange number. And yeah, rational number would be any ratio of integers, like 71 divided by 2 or something like that. But it's not even like that. It's some strange number. And you cannot, if you try to fit them around an edge, well, you can fit 5 of them, but then you're left over with this gap and you can't fill it with another tetrahedron. And so there's no way, and I mean, you don't have to do it this way. You could also try, you don't have to match them up face to face, but even if you don't do it that way, you'll see that it's not possible no matter how you try to put them together, there'll be a gap. So this regular tetrahedron, so Aristotle's wrong. So the regular tetrahedron does not fill space. But what happens if you look at other shapes of tetrahedra, like a non-regular tetrahedron? Could it be that there's some non-regular tetrahedron that fills space? And the answer is yes. And to explain this, let me imagine this. Suppose I start with a cube, say the cube in 3-dimensional space, where you look at the points where the x, y, and z coordinates are each ranging from 0 to 1. So that gives you a cube. And you can divide the cube up. You can divide the points of the cube into 6 categories according to which of the coordinates is the largest. For example, there will be some points in the cube where the x coordinate is the smallest and the z coordinate is the largest. And there'll be other points in the cube where the y coordinate is the smallest and the z coordinate is the largest. And so in this way, you can divide up the cube the points into the cube into 6 categories according to which of how the coordinates are organized. And if you look at the points that belong to one of these categories, like this category, then that actually turns out to be a tetrahedron. And the same for all the other possible orderings. So depending on which coordinate you want to be the smallest. And just because of the symmetry of the problem, all these tetrahedra they're all the same shape. So they're all congruent to each other. So this argument shows you can divide a cube into 6 congruent tetrahedra. And once you've done that, so you can think of it the other way around. You can start with this one tetrahedron and then say, okay, I can take 6 copies of those and fill up a cube. And then once you have a cube, you can just take copies of this cube and fill the whole space with those. And so at the end, you'll get a filling of the entire space by tetrahedra that are congruent to this original one. So this is a tetrahedron that does fill space. It's not a regular tetrahedron. I mean, you can see that some of these edges are longer than others. Like some of them are square root of 2 and some of them are only 1. But yeah, and I guess there's one that's even square root of 3. But anyway, so it's not regular, but you can fill space with it. And so now so you can now ask the question, what other non-regular tetrahedra can you fill space with? Is this the only one, or are there others? Well, there are others. So here's another thing you can do. So imagine taking this cube and look at these 3 vectors. But now imagine this is like a tripod, and imagine you start closing the tripod. So these vectors, they stay the same length, but the angles between them become smaller. And so you get these 3 vectors, and the angles between them are all the same, but they're now less than 90 degrees. And as you close the tripod, the cube deforms as well. It becomes this parallelepiped, where it's formed out of sides that are all, yeah. So it's like changing a coordinate system. And now if you look at the 6 tetrahedra that we had on the previous slide that filled up here, you can deform those as well. And they'll give you 6 tetrahedra that fill up this thing. And so I'll show you one of them. So this is what happens to the green tetrahedron that we had on the previous one if you do this closing up of the tripod. And well, here's a formula for it if you know about vectors. But anyway, the point is that this tetrahedron, if you take 6 copies of it, you can fill up this parallelepiped, and then you can fill up the rest of the space by taking copies of that parallelepiped. So this gives you not just one tetrahedron that works, but it gives you an infinite family of tetrahedra, such that each one can be used to fill space. Yeah, so you get this. Yeah, so so I'll call it a 1-parameter family. Actually, it's actually more than 1-parameter family, because you could also enlarge the size of it. But I'm not counting that. I'm really just looking at the shape, not so much the size, since the size doesn't really matter as far as whether it fills space or not. So yeah, so this gives a 1-parameter family. And so, well, now you can ask again, are there any more besides this? And it turns out, yes, yeah, so there are some more. And the first problem that I mentioned on the first slide is to describe all the possibilities, all the possible tetrahedra that can fill space. And so far, people have discovered not just that one infinite family, but there are actually 3 infinite families. And these were actually discovered in 1895, but I think it wasn't actually noticed that some of them actually can fill space until 1974. Anyway, these have been known for a long time. And in addition to those 3 infinite families, there are two isolated tetrahedra. So I'll call them sporadic just because they're just sort of by themselves. They're not part of any family that we know of. And those were also discovered a long time ago. And since then, there haven't been any more discovered. And so there's a question, are those the only ones? And are there more tetrahedra that can fill space? And nobody knows. So even now, so we don't. I mean, even after our work, we still don't know. So that's where this problem stands. I mean, in some sense, this problem is over 2,000 years old, but we still don't know the answer. And it's very. I mean, you could tell us. Yeah. Okay.
Can I ask a question?
Yeah, go ahead.
Can you say a word about why the 1-parameter families depend on 1 parameter?
Oh, okay. So the question is why there's 1 parameter here. So one way to think about the parameter is you think about the angle between these two of these vectors. So in the cube, the angle was 90 degrees. But as I close up the tripod, that angle is what I can use to describe which tetrahedron I'm talking about. And so that angle, I can change it to be from anywhere from between 0 and 180. Or no, not 180, 0 and 120. So the maximum I can open the tripod is if, as it opens almost fully, the angles become close to 120. So I can choose any number for that angle. And then once I have the angle, then that tells me the shape of this tetrahedron. So that's what one parameter means, that each tetrahedron in this family is described by a single number. Okay. All right, so let me move on. So we said nobody knows the answer to this question. Let me move on to the second question now. So the second question is about what's called scissors congruence. So here I have, if you look at this triangle and the square, they're definitely not congruent, because congruent means they have the same shape and size. So I want to ask you, do they have so which one has greater area? Anybody want to guess?
I'll guess the left one, since I'm the only one that can speak.
Okay, well, I mean, that's what I would have guessed too by looking at it. But actually, well, let me give you a hint. I mean, it kind of looks like the triangle is bigger in terms of area. But here's a hint. Suppose I cut up the triangle this way. So, and now imagine you take this point and you rotate the red triangle 180 degrees around that point. So look at what happens. And do the same thing with the purple triangle. So, yeah, well, well, this is, I mean, I hope this is a proof. This is one way I could convince you that these things have the same area. So if you can cut up one of them and reassemble the pieces into the other one, that's what scissors congruent means. That after cutting it up, you can reassemble the pieces to get the other one. So this triangle and this square are scissors. This triangle is scissors congruent to this square. They're the same area. Now, okay, so but this is just one triangle and one square. Suppose you had two other shapes. Suppose you had two polygons, maybe with more sides. And well, I mean, they're going to have to, if you want to be able to cut one up and reassemble it the other, they better have the same area. So, but is that the only condition you need in order to be able to do this? If I want to reassemble this triangle into a hexagon, could I do that? And the answer is yes, you can. So this was discovered a long time ago, that there's a method. If you're bored by the talk, you can try to figure out how to do this. It's a little bit tricky to figure out a method to do this in general, but yeah, it's just been known for a long time. Okay, so now this is the two-dimensional problem, but now let's move up to 3 dimensions, and instead of looking at triangles, I'm going to go back to a tetrahedron. And so this is a question that was raised by David Hilbert in 1900. So he was one of the most famous mathematicians around the turn of the century. And in the year 1900, he made a list of 23 problems that he thought were the most important problems in math for the mathematicians of the next century to work on. And this was number 3 in his list. Just deciding questions like this: is every tetrahedron, can you always cut it up using pieces into, cutting up by planar slices like this? And can you always cut it up and reassemble the pieces to make a cube? And the reason he was so interested in this, the reason he thought this was so important, is that, well, if you could always do this, that would mean that you would have a method for computing the volume of a tetrahedron. You could compute it by just cutting it up and reassembling it into the cube, because you already know what the volume of a cube is. And this would be in some ways, it'd be a conceptually simpler way to explain the formula for the volume of a tetrahedron. I mean, you maybe remember that the volume of a tetrahedron is 1/3 base times height. But the way that's proved, the way that was proved by the ancient Greeks, was by inventing something that's kind of like calculus. They approximated the tetrahedron by slicing into many pieces, and they essentially did something like integration to get upper and lower bounds to do that. So it's a sort of a complicated method. So that's why, so this is a question about the foundations of geometry. Could you actually understand what volume is just by, just cutting and reassembling? Okay, so he asked this question. He said, this is going to be one of the most important problems for the next century mathematicians to work on. And then his former student in the same year, he just answered the question. He found out that he said, no, the answer is no, you cannot. In particular, there, I mean, not volume must be preserved when you try to reassemble something. But what Dane discovered is that there's another quantity beyond just volume that also must be preserved when you cut up a tetrahedron and reassemble it. I mean, I'm not going. This is really for the mathematicians. Don't worry so much if you don't do. Anyway, the point is, it's some quantity that's built out of the lengths of the edges and the dihedral angles of the edges. It's some combination of those. And whenever you cut up a tetrahedron, this quantity stays the same. The total amount of this quantity, just as the total amount of volume stays the same. And so, but if you look at this quantity for a regular tetrahedron and for a cube, they're different. One of them is 0 and the other one's not 0. And so this invariant distinguishes, it shows that these cannot be scissors congruent. Okay, so at least the regular tetrahedron cannot be cut up into finely many pieces. You cannot and reassembled into a cube. But maybe there could be some other tetrahedra that could be reassembled. And it turns out, yes, there are some other tetrahedra that some tetrahedra can be reassembled into a cube. And so now the question, so the problem too is to describe which tetrahedra can be cut up to make a cube and which ones can't. And so there's a partial answer to this that is in terms of this Dane invariant. I mean, for any given tetrahedron, you can easily test whether it is or is not congruent, scissors congruent to a cube. You just have to compute this invariant. But the real problem then is to describe them all. Like, what are the tetrahedra that have this invariant equal to 0? And again, just as in problem 1, there's some infinite families. There's some one parameter families, and there are also there's some sporadic examples. But can we list them all? That's the question. And again, nobody knows. Nobody knows how to do this. Okay, so all right. So in some sense, Hilbert's question is not completely answered. So yeah, okay. So that's problem 2. So now let me move on to the third question. Okay, so the third question is about dihedral angles, but again, I'm going to start with the 2-dimensional version. So because the 2-dimensional version is always a lot easier. So for this, we're just talking about a triangle, and we're just talking about the 3 angles of a triangle. And well, you probably know something about the 3 angles of a triangle. They always add up to 180 degrees. And that's the only condition. If you have, well, they have to be positive too. So they have to be positive numbers. But if you take any 3 numbers that add up to 180 degrees, you can build a triangle that has those angles. And so, well, so for example, if I give you probably have seen this kind of problem in high school. So if I give you, okay, except maybe not with these weird numbers, but here's a rational number. It's a fraction, 180 divided by 7. And if I give you that, if I tell you this angle is this and this angle is this, then I think you know how to figure out this angle. I mean, you just have to figure out what makes them add up to 180. So it turns out to be this, because this is 1/7 of 180 and this is 2/7. And so this has to be 4/7 of 180 in order for them to add up to a whole 180. Yeah, and in general, if you want to describe all the triangles, all the possible angle triples that a triangle can have, well, you can choose the first 2 essentially arbitrarily, and then the third one you can solve for. It's going to be 180 minus those 2. And the only condition on these numbers is that they all need to be positive. Okay, so this is a 2-parameter family, because the parameters are, you choose your number x and your number y, and you get a shape of a triangle. And again, I mean, you can have different sizes. I mean, the angles don't determine the triangle because you have different sizes. But as far as the shapes are concerned, this is a 2-parameter family. And if I ask you for the problem where I don't want just any old angles, but I want each angle to be a rational number, such as in this example, that's also easy to do, because if I choose x and y to be rational numbers, then this third angle will also automatically be rational. So here, I can get a parameterization of all the triangles that have rational angles. Okay, so that's what happens in 2 dimensions. Now, what happens in 3 dimensions? So now I want to look at, this is the third problem, And this is to describe all the tetrahedra such that all 6 of the dihedral angles are a rational number of degrees. Each of the angles is a rational number of degrees. So, okay, so this also has a long history. So prior to our work, there's a one parameter family known. It actually was the same. It's the same one that came up with that tripod that I showed you earlier, except for special values of the parameter. It turns out that those tetrahedra have rational dihedral angles. And then over a period of many years, people found every couple of years, people found a new tetrahedron that also had this property, but was not part of this family. And so 15 more were discovered over this time. And then, well, a long time passed with no new ones being discovered. But then I and my co-authors last year, so this is a paper we posted in December last month. Not only did we discover a new one parameter family, so there are actually 2 one parameter families, but we also discovered 44 new sporadic tetrahedra that were not part of these, that were not previously known. And not only did we discover these things, but the real part of our work is to show that this list is now complete, that there are actually no others. So the complete answer is that there are these 2 one parameter families and these 59 sporadic tetrahedra. So there's never going to be a 60th one. Okay, and so yeah, so the way to read this is that, so you notice that each of these things is a 6 tuple of numbers, but it depends on this x. So what you're supposed to do is you choose your favorite number, x. Well, it should be a rational number that's between 30 and 90. So you could take x could be like 35 and a half, say. And then you plug in x equals 35 and a half, and then you get this 6 tuple of numbers. And then the claim is that those 6 numbers are the dihedral angles for some tetrahedron. Okay, so this is the complete answer to the question. So I want to explain how do you actually prove something like this? How do I know that there are no? I mean, maybe it's not too surprising that you could write down some of these tetrahedra and check. You could just build the tetrahedra and check that there actually is a tetrahedron with those dihedral angles. But how do you actually show that there are no others? So yeah, so let me start to explain that. So first of all, maybe before you look at this, remember for triangles, if I give you 3 numbers and I want them to be the angles of a triangle, all you have to do to know that they come from a triangle is check that they add up to 180 and that they're positive. So, so there's a condition on the 3 angles, but it's a very easy one for a triangle. You just have to make them add up to 180. Now for 6 angles of a tetrahedron, it's a lot more complicated. The actual condition on those 6 angles, I mean, you can't just specify any 6 angles. They have to satisfy a certain equation. And that equation involves this 4x4 matrix where you plug in the cosines of the 6 angles. So yeah, so theta 1, 2 means the dihedral angle between face number 1 and face number 2. So there's 6 of those, and then you plug them into this matrix, and then you take the 4x4 determinant of this matrix. So if you know what a determinant is, then yeah, that's going to be some expression that involves products of these cosines and adding up to 0. And so that's the equation. Yeah, and then there's some inequalities so that these things have to satisfy, just analogous to the fact that in the triangle, the angles have to be positive. So, okay, so the task then is to find all the solutions to this equation where each of the 6 variables has to be a rational number of degrees. Okay, so this is why this is a harder problem than in 2 dimensions, because it's not like theta 1 plus theta 2 plus theta 3 equals 180. It's like this messy mess equals 0. Okay, so how do you actually study this? So the strategy is to, well, one thing that makes this complicated is that it involves this complicated function called cosine. And so one way to get rid of the cosine is to use complex numbers instead of these angles. So let me say a little bit about this. So here's a picture of the complex plane. So this is a plane where every point in this plane corresponds to a number. So the real numbers, so 1, 2, 3 are along this line. So this would be -1, this would be 0 along this line. And then on this axis, there's I, which is the square root of -1, and this would be minus I down here, and then way up here off the screen would be 2 times I, and then you could take things like 1 plus I would be this point here, and then 2 plus I would be here, and yeah, so you have all these points. But now suppose instead of taking this number here, I, which is at sort of at 90 degrees from around 90 degrees around the circle, suppose I only went 72 degrees around the circle. So that's 72 is 1/5 of 360. So it's 1/5, it's going 1/5 of the way around the circle. So that's some other complex number z that corresponds to that angle, which this theta is just 72 degrees. And if you take that number and you multiply, if you square that number, because of the way complex numbers square, if you multiply by z, that rotates by this angle. So if you take z squared, it's going to be over here, and then z cubed will be here, and z to the 4th will be here, and so on. And when you get to z to the 5th, it comes back to 1. So z to the 5th is equal to 1. And because of that, because z to the 5th is equal to 1, is the number z is called a 5th root of unity. Just like a square root of 3 would be a number whose square is 3. If you have a number whose 5th power is 1, then it's called a 5th root of 1, or 5th root of unity. And well, once you know this, you can also say, I mean, if you divide this by z, then you'll see that z to the 4th is also the same as z inverse. So you could also call this point z inverse. And you can see if the relationship with that and this one is that it's the sort of mirror reflection. Let me put one other number in this diagram. So this red point is another number. You can see it's a real number since it's on this real axis. And now there are 2 ways you can describe what that number is. So one way would be to look at this right triangle here and use trigonometry and to say, well, this is the length 1. And so if you remember your trigonometry, that red length is going to be cosine theta. But on the other hand, this point is the midpoint between z and z inverse. And so you can also say it's going to be the average of z and z inverse. And so, yeah, so this gives you a relationship between the angle theta, which in this example was 72 degrees, and this complex number z, which is a root of unity. And so this lets you replace the cosine of the angle by something that's in some ways, even though it's complex numbers, it's actually simpler because it doesn't involve this complicated function cosine, it just involves some number whose 5th power is 1. And that's easier to deal with. And so you can do this with any rational number of degrees. If you have any theta that's a rational number of degrees, you'll get some kind of root of unity. Maybe not a 5th root of unity, but it'll depend on what this denominator is, what kind of root of unity it is. Okay, so we're going to use this equation now, the boxed equation, and we're going to take now if you take this equation we had on the previous slide, this one, you can use that to replace each of these cosines by roots of unity. And so what you end up getting when you do that is you get an equation in a lot of different z's. Instead of 6 angles, thetas, you have 6 complex numbers z's. And then the equation becomes now essentially a polynomial equation. And it's still a complicated equation. I mean, each of these is representing in fact, it's more complicated than it looks like, because what this sum means is you're supposed to take a symmetric sum over all the possible permutations of the numbers 1, 2, 3, 4. And also you're supposed to take all the possible signs independently, plus or minus 1 in each of these sums. So there are actually 105 terms in this sum. So it's not an easy equation, but now at least it's a polynomial equation. There are no cosines. That's what's been gained. instead you have to solve this equation, but it's a funny kind of equation to be solved, because you're solving the equation, but you have the constraint that each of the 6 numbers, each of the 6 z's, has to be a root of unity. And so it's a kind of problem that you're not used to in high school algebra, because usually you're just trying to find all the real number solutions to some equation. Like, you like x squared plus y squared equals 1. Oh, that's a circle. But here you have this extra constraint that the variables are supposed to be roots of unity. And so this is now, because it involves these roots of unity, it's partly a problem in algebraic geometry because of this polynomial equation, but it's also a problem of number theory because of these roots of unity that are appearing. And there have been methods developed, starting in the 19th century, for solving equations like this, but never as complicated as this one. So the methods that were developed over the past 150 years, they seem to work for equations where you had at most 3 variables, or equations where you had at most 12 terms. But ours is quite a bit worse than that. It has 6 variables and it has 105 terms. So it might seem that this is going to be hopeless, but we were able to improve upon these methods. We combined these 2 methods and improved them by developing some extra number theory of our own. And we also took advantage that we now have more powerful computers. And we use computers not only to search for solutions, but actually to analyze the cases that arise in the proof that there are no other solutions. And so by doing all this, and by doing several large computer calculations, we were able to find all the solutions to this, where the variables are roots of unity. And so once you have that, then that tells you all the tetrahedra that have all 6 of their dihedral angles rational. Yay! So problem 3 is solved then. Okay, obviously I've skipped over a lot of the details, but I just want to give you a sense of what was involved in solving this problem. All right, so let me now say something about these 3 problems. So far I've been presenting the 3 problems as if they were 3 separate problems. But actually these problems are related to each other. And that's another reason why we're interested in all 3 of them. So it turns out that, so this is a Venn diagram. It turns out that every tetrahedron that fills space is also scissors congruent to a cube. So if you have a tetrahedron that fills space like that, like the ones that I put into the 6 tetrahedra that I put into a cube earlier, that one must also be able, you can also cut it up and make it into a smaller cube. And it's also true that if you have a tetrahedron that has rational dihedral angles, like the ones that we just classified in problem 3, those also are scissors congruent to a cube. And so here I'm going to make a diagram where each point that I draw in this diagram is going to represent a tetrahedron. So it's like it's like a symbolic kind of diagram. So here's what Aristotle thought. He thought that the regular tetrahedron could fill space. So if that were true, you would put this regular tetrahedron, this dot represents the regular tetrahedron. That would go there. But well, that 1800 years later, as I explained, that was proved to be wrong. And so I'm just going through the history a little bit. So in 1895, Hill discovered a couple of families of tetrahedron that filled space. So each of these dots, as I mentioned, is one tetrahedron. And if you see this like curve thing, that means that there's one tetrahedron for each point on that. So this is a 1-parameter family. So he actually found 3 1-parameter families of tetrahedra that can fill space. And then, okay, so Dane solved Hilbert's 3rd problem, and he proved that the regular, contradicting what Aristotle said, he said, okay, he proved that the regular tetrahedron is way out here. It's not even scissors congruent to a cube. Okay, so in 1923, another mathematician found that there's another tetrahedron that can fill space. Then this is another sporadic one. And then over the next couple of years, next couple of decades, a bunch of other tetrahedron, no more that tiled, but a couple more that had rational dihedral angles. So these are, and some other ones that were scissors congruent were found. And then some of us came, and so 25 years ago, yeah, maybe I should have said, I mean, we started this project actually 26 years ago. It took us a long time to finish it. So, but we kind of knew already back in 1995, by doing some computer searches, we had found these all these 59 of these ones with rational dihedral, and we also found this new one parameter family. But we didn't know, we could not figure out whether these were the only ones. And so it was only last year that we finished this by doing what I explained on the last slide with these roots of unity, that we finished the argument to prove that at least this blue circle, this blue oval is now complete. We know exactly what belongs in here. And along the way, we also found some extra one parameter families of tetrahedra that are scissors congruent to a cube. So yeah, so this is where things stand. Actually, I should say, we don't actually know about all these tetrahedra here. We don't know whether they can, some of these might actually fill space. It's actually kind of hard to tell whether, if I give you a particular tetrahedron, it's maybe, sometimes it's hard to tell whether it can or cannot fill space, because there's so many ways you could try to put them together. So yeah, so this is where things stand as far as this problem goes.
May I, before you go off the slide, there's a lot of questions about what Dane invariant zero means. Can you say a word or two about how it fits into this taxonomy?
Yeah, so Dane invariant zero turned out to be the exact condition for a tetrahedron to be scissors congruent to a cube. So when a tetrahedron has Dane invariant zero, that means it's scissors congruent to a cube, and vice versa. So if I were to draw a bubble here for all the tetrahedra that had Dane invariant zero, it would be the same as this outer bubble. So all these dots in here, all these tetrahedra, they all have Dane invariant zero. And the regular tetrahedron does not have Dane invariant zero. That's how we know that it's not scissors congruent to a cube. Okay?
Thanks.
All right, any other questions? This is a good time for questions, so. Okay, let me move on then. Since there's a little bit of extra time, let me talk about a bonus problem besides the three that I've been discussing that can also be solved with our methods. So here's the problem. Imagine you have a sphere and you want to place cities on it in such a way that the distance between any two of them is a rational number times the circumference. And when I talk about distance, I'm talking about distance along the sphere. Like for example, if I take this city at the North Pole, okay, maybe there's not a city at the North Pole, but anyway, this is some alien world, so ocean world or something. Yeah, so if you have some city at the North Pole and you have some city on the equator, then you're not allowed to, when I'm measuring the distance, you're not allowed to burrow, you're not allowed to go through the ocean to go there. You have to go along the sphere. And so the distance here is 1/4 of the circumference. Because if you went all the way from here to the South Pole, that would be half the way around the sphere. But going to the equator is only 1/4. So those two cities would be allowed, since that number is a ratio of integers. It's 1/4. And so you could imagine putting a third city. Maybe you could put, for example, if I had a city here that was like 1/10 of the way from this one along the equator, I could put a city there, because not only would that be 1/10, but the distance from here to here would also be 1/4 again. So those three cities would be allowed. And so the question is, how many cities can you place on a sphere, and such that every pair of cities is a fraction like this? Okay, so let me show you one way you can generate 4 such cities on a sphere. So here's one possible construction. if you start with a tetrahedron that has rational dihedral angles, and then you put a sphere inside it. So, and you inscribe it, and that means that the sphere it's inside the tetrahedron, but it's touching each of the faces. So it's tangent to each of these triangles. So yeah, and then so each of these sides touches the sphere at one point, and so those are called the tangency points. And so you get this one in the front, you get this one on the side, and this one's underneath the sphere, so you're actually looking at it through the sphere. So that's why it's purple instead of red. And then there's also this other one is touching the back side of it, is touching the back side of this. So you get those 4 points in a sphere. And what you can check using some easy geometry is that if the dihedral angles of this tetrahedron are rational, then the distances between these cities will also be rational. And this gives you, well, this and some related constructions essentially gives you all ways of constructing 4 cities on the sphere that have rational distances. So using the solution that I showed you for finding all the tetrahedra with rational dihedral angles as a byproduct, that also solves this problem for 4 cities on a sphere. Okay, so we know all the 4 city configurations. And now the question is, well, suppose you had more than 4 cities. Suppose you had 5 cities. And you want to know all the possibilities for placing 5 cities on the sphere. Well, if you had 5 cities, then if you choose any 4 of them, like those 4 red ones, then those 4 red ones must be in the previous classification. Those, you just ignore the 5th one, and then the 4, just all the distances between these 4 must be rational. So this must be related to some tetrahedron. And so we know what the possibilities for those 4 are. And so, and the same holds for all these other, if you choose these 4, if you exclude a different one, and so on and so on. So you could do this for any 4 of them. And you could try to reverse the process. If you didn't know what the possibilities for the 5 cities were, you could try to start with all the possibilities for the 4 cities and try to piece them together to make a 5-city solution. And so this is what we did. So it's a little bit complicated because there are a few hundred possibilities and these infinite families for the 4 cities. But so it's not something you'd want to do by hand, try to match up these 4, this is the possibilities for these 4, this 100 possibilities here with 100 possibilities here, and so on. But it's something that a computer could do. And it turns out that, yeah, we used a large computer calculation to piece these together, and we were able to find all the 5-city configurations too. And maybe you can guess what's coming next. If you can do that, if you can use the 4-city solutions to find all the possibilities for 5 cities, you can do the same thing with 5 cities to get all the 6-city solutions, and so on and so on. And you can keep going. And you might think, oh, it's going to get more and more complicated as you do this. But actually, something nice happens. Once you get a lot of cities, it becomes much harder to put in an extra city, because if you've got 17 cities already, that 18th city you put in, it has to have rational distances to all the first 17. That's a lot of conditions. And it turns out that once you get to enough cities, the only solutions that you get are of a very limited type. So we actually, once you get far enough in this calculation, you start noticing a pattern. And so because of that pattern, we were actually able to understand what happens all the way down. I mean, even though the computer had to stop somewhere, we were able to analyze it theoretically to figure out what happens for any number of cities. And so we were actually able to prove a theorem that describes the possibilities for any number of cities. And the final answer is kind of complicated, because even for 4 cities, as I told you, there are a few hundred possibilities, and so on and so on. So I'm not going to list them all for you, but I'll show you a sample of what comes out of this, of what you can deduce from this theorem. So, well, here's one way to make a configuration. you could take, okay, so here you take a sphere, and along the equator, you put some number of cities equally spaced along the equator. So maybe you put, yeah, maybe you put 20 cities along here. So then the distance from each one to the next one is going to be 1/20th of the circumference. So that's okay. And also the distance from this one to this one would then be 3/20ths. And if you want to, you can also put, that's not all you can do. You can also put a city at the North Pole, because that will be a distance of 1/4 from each of these equator cities. And you can also put one at the South Pole. That's okay too. So that's one possibility. So you can actually get as many as you want. Because you can start with n equally spaced cities on the equator, and then have 2 more on the North and South Pole. But what we showed is that if you don't have a configuration that's contained in one of these that looks like one of these, then the maximum number of cities it can have is 30. And not only that, but if there are exactly 30 cities and they're not part of this, then they must be at the vertices of what's called an icosahedron. So that's this shape here. So this is some sort of hybrid between the icosahedron and the dodecahedron. So it's something you can get by taking an icosahedron and you take the midpoints of all the edges, and you could take those midpoints to be the cities. And so that gives you these 30 things, and that you can, if you have those as your cities, then it turns out that the distance from here to here turns out to be 1/10. And yeah, and the distance from here to here, I don't remember them all, but I think this one may be, okay, I don't remember. I think maybe this one's maybe that, what is that, 1/6 or something? Okay, anyway, I think this one's 1/4, and then, yeah, so anyway, it all works out. So yeah, so that's an example of what we could deduce just using, yeah, and it was a big I mean, it was a large computer calculation to get up to, because you had to go all the way to 30 cities to piece them together. And we got this by piecing together these 4-city solutions. In fact, we didn't even know what the answer was going to be. We didn't even know about this. We didn't even notice this 30-city configuration to begin with. It's just that once we started piecing together these 4-city configurations, eventually we started noticing this pattern, and we started trying to draw this on a sphere and see, oh, it kind of looks like an icosahedron. And so we actually sort of discovered, it sort of came out of the calculation sort of organically. It came out like this. Okay, so that's this bonus problem. All right, so let me end here by summarizing what everything that we've talked about here. So on the first slide, I mentioned there are these 3 old questions about tetrahedra. So the first one was about which tetrahedra can fill space. Some of them, like the regular tetrahedron, cannot, but other ones can. And we still don't know which ones can and which ones can't. So that's still unsolved. The second problem is about which tetrahedra are scissors congruent to cubes. So which tetrahedra can you take and slice with finitely many planes and reassemble pieces into a cube? And this one, again, it's not known. And the third question is, which tetrahedra are such that all 6 of the dihedral angles are a rational number of degrees? And so this one is the one that we've solved. So happily we were able to do something here. Yeah. So this, and now so what do we do? What's the future of this then? Well, we have I'm working with a team of 40 MIT undergrads right now. That we're starting to work on the first 2 problems, using some of the insights we've gained through studying the third problem. And we're also using, when they're also being helped by some of the MIT research scientists that are part of the Simons collaboration in arithmetic, geometry, and computation. So some of them are really experts on doing large mathematical computations. So we're hoping that we're going to make some progress on these even older, these first 2 problems. And well, it remains to see what we'll do.